Hello, welcome to week 4 review for AP Environmental Science. This week's review is going to focus on Science Practice 6, applying quantitative methods to addressing environmental concepts, and practice with free response question 3, where you have to analyze an environmental problem and propose a solution doing calculations. Now, the good news about the third question on the free response section is that regardless of whether or not you can maybe remember the information or the content that the question's asking you about, if you can do these math procedures, you are almost guaranteed at least 2 or 3 points on that question. So let's start with a review of metric conversions. Earlier in this unit, this was sort of introduced to you or reintroduced to you if you've seen it before. And the good news about these metric conversions that have to really be committed to memory is that there's only a few that tend to pop up on the AP exam or that really have to do with the calculations required for AP Environmental Science. And even of these, the milli, centi, deci, deca, hecto, kilo, and mega, the ones that I see more often are these and these. So if you are highly proficient in conversions between these 4 units, that's a good indicator that you'll be able to successfully do the calculations for this test. The second thing we want to review before we get into some practice is scientific notation. So oftentimes in APES, we are dealing with really large quantities or really, really small. So talking about millions of acres of land or thousands of gallons of water. Or we could even be talking about very, very small amounts of mass for precious metals. So being able to use scientific notation and then to also add, subtract, multiply, and divide using scientific notation will be very, very important for your ability to correctly answer those questions. So a quick review on how you deal with exponents when you're doing adding, subtracting, multiplying, and dividing. So for addition and subtraction, the base has to be sort of equal to each other. So the power of 10 in each term has to be the same. And then you can do the operation just like you would do normally. So here in the example, the two numbers are having the same exact exponent. That allows you to add those, the same as you would normally. With multiplication, you don't have to do this. But what you'll do is you'll just add the powers together to get a new exponent. So you would multiply these numbers normally like you would, and then you just add the exponent. So 4 plus 2, that gives you 6. So with division, it's the same kind of idea, except you are subtracting those powers. So you would divide 8 by 2, not like you normally would, to get 4, but instead of adding the 7 to the 4, you're subtracting 4 from the 7, and that's how you end up with 3. We'll do a few practice problems involving this in a minute. So there are a few test-taking habits that would be good to keep in mind for completing question 3 successfully. So I call them habits because if you can get into the habit of doing them now, especially during labs or other types of work where you're doing calculations, then it will become almost like a reflex by the time you are ready to take the test. So the first 2 have to do with showing your work. So oftentimes the rubric for these questions will give you points simply if you just show how you set up the problem. Now you'll probably be able to get the right answer because you've got your calculator and you're setting up the problem correctly. But just in case, it's always a good idea to show how you are attempting to solve the problem. That always includes the proper use of units as well. Again, sometimes the rubric will give you a point even if you did not say the proper units in your answer, but we want to make sure that we're going to get the point, so it's always a good idea to include units the entire time. The other habit to get into is using that scientific notation. It feels like it's kind of weird and a little bit pointless, but again, we're usually using really big numbers or really small numbers. And so, especially if you have to write that number multiple different times, it can save you a lot of time. So, say you're having to deal with something that's, in the millions, right? So if you had to spend that much time writing that number multiple times during your calculations, then that's just wasting your time for actually answering the question. It'd be much faster to just write it out in scientific notation, and that will also make your calculations easier down the road. Now, there are also some test-taking musts that will really help you out with question 3. Now, one, of course, being proficient with dimensional analysis, which you're probably already practicing, and then also being able to recognize and be able to convert units of area and volume. So let me give you an example of what I mean. So we know from our metric conversions table that 1 meter is equal to 1,000 millimeters. So that's in, this one dimension of length. Now, if we're looking at area, we have meters squared, but that also is coming from the fact that we are multiplying 2 different dimensions, right? Length and height, in order to get the entire area here. So when you convert from meters squared to millimeters squared, it's not just a one-step conversion. You actually have to think about squaring the 1,000 as well, which makes the amount of millimeters like that much more than it would have been in just meters. So this also happens when we're looking at volume. So 1 meter cubed isn't just 1,000 millimeters cubed, because you also are cubing the meter as well as the millimeters here. So we have to do 3 times 3 times 3, which is actually 10 to the 9 millimeters cubed. So that can be something that creeps up on us in our conversion. So we just want to make sure that we are being mindful of that. The other important thing to be able to do is calculate percent change from memory. So just to kind of review, percent change is where you've got some change over time. And so you've got the final value, and you're going to compare that to the initial value, what you started from. And you are calculating the percent change from that initial value. So you want to divide it by the initial value. And because it's a percent, we have to multiply by 100. And then that can give us percent change. More on that later. So let's get into some practice. This first question is testing your ability to read a graph and then to create ratios between the 2 types of things that are displayed in the graph. So let's see what they want us to do. A, determine the net change in atmospheric CO2 concentration between 140,000 years ago and 125,000 years ago. Calculate the ratio of the change in mean global temperature to the change in atmospheric CO2 concentration between 140,000 years ago and 125,000 years ago. And then finally, scientists predict that between 1950 and 2050, the atmospheric CO2 concentration will increase by 200 parts per million. Predict the change in mean global temperature between 1950 and 2050 using the ratio that you calculated in Part B. Now, this information has not been covered yet at this time during the year. You won't actually start talking about atmospheric CO2, global warming, and change in the climate until the last unit. But you don't need to know anything about that in order to do these problems correctly. So let's take a look more closely at the graph. So A wants us to determine the net change in atmospheric CO2 concentration. Basically, how much did it increase or how much did it decrease? So let's take a look at the graph. Where is 140,000 years ago? Well, this is 150,000 years ago for CO2, So 140 is right here. So now I'm just going to look and see at what point during 140 that line meets the year and draw it over. So at 150,000 years ago, there were 200 parts per million of CO2. I also need to know what this is for 125,000 years ago. So I have 100, 110, 120, and then 125 is in the middle here. So again, I'm just going to draw my line up and draw it over. And that gives me about 280. So 140,000 years ago before the present, it was 200 parts per million, and that was 140,000 years ago. 125,000 years ago, it was 280. So what is the net change? Well, 280 minus 200, that gives me an increase of 80 parts per million. And already, just by being able to read this graph, I've got at least a point on this question. So let's look at B. Calculate the ratio of the change in mean global temperature to the change in atmospheric CO2 concentration between 140,000 years ago and 125,000 years ago. So here's that word, ratio. So let's make sure we understand what it is that they're talking about. They really want us to make a direct comparison. So CO2, 2 degrees Celsius, because now we're looking at global temperature. So do we already know what the parts per million change was from part A? Yes, it was 80 parts per million. So now let's focus on this part of the graph to get our change. So again, 140,000 years, that was right here. And that gives me -8 degrees Celsius. And 125,000 years ago, that gives me about 2. So -8 degrees Celsius for 140,000 years ago, and +2 degrees Celsius from 125,000 years ago. So what is the actual change? 10 degrees Celsius. So in the same time period that we got for the CO2 concentration change, we now know that there was an increase of 10 degrees. But we have not answered the question yet because we still need to know what the ratio of the change is. So we know we had an increase of 80 parts per million from part A, and now we plug that into our information about the temperature change. So 10 degrees Celsius divided by 80 parts per million, that gives me my ratio of degrees Celsius to CO2 concentration. So for every degree Celsius change that there was also an 8 parts per million CO2 change. Scientists predict that between 1950 and 2050, the atmospheric CO2 concentration will increase by 200 parts per million. Predict the change in mean global temperature between 1950 and 2050 using the ratio that you calculated in Part B. So what was that ratio that we calculated in Part B? 1 degree Celsius for every 8 parts per million of CO2. Now, we already know as well that they think that there will be an increase of 200 parts per million. So in order to make this prediction, we just multiply the ratio that we calculated in Part B by what they gave us in the question. And that is a 25 degrees Celsius increase in global temperature. 200 divided by 8. So we didn't have to know anything about climate change, greenhouse gases, historical climate data. We didn't really need to know about that. We just needed to be able to pick the data out of the question and make the calculations correctly in order to get these 3 or 4 points on this question. The next practice calculations question focuses on the use of percent change and scientific notation. So approximately 30 million mobile devices were sold in 1998 in the United States. the number sold increased to 180 million devices in 2007. So already you can see that we're working with some pretty large numbers. A, calculate the percent increase of mobile device sales from 1998 to 2007. B, each mobile device sold in 2007 contained an average of 0.03 grams of gold. Calculate the number of grams of gold that were used in the production of the mobile devices sold in 2007. So now we've got some big numbers in the millions, and now we've got some really tiny numbers as well. Assume that the average mass of each mobile device was 0.1 kilograms. The United States Environmental Protection Agency estimates that about 10% of the mobile devices sold in 2007 were recycled. Calculate the mass in kilograms of the mobile devices sold in 2007 that were not recycled. So this question is really about solid waste management, e-waste, and recycling practices. But again, this is a math question. We just need to be able to do the calculations correctly. Let's take a look at A first. So we need to calculate the percent increase of mobile device sales from 1998 to 2007. So the first thing that I want to do, of course, is convert these really large numbers into scientific notation. So 30 million becomes 3.0 times 10 to the 7, and 180 million becomes 1.8 times 10 to the 8. And that's because million, that's 10 to the 6, and then I know that I'm adding 2 here and then just adding 1 there. The other thing that I want to remember is how to calculate percent increase. So remember, that's going to be final minus initial over initial times 100, and that'll be giving us our answer in percentage. So what is my final number? My final number is that happened in 2007, and my initial is that happened in 1998. So let's see how you would set this up. So I have my 1998 number, and then I have my 2000 number. So 1.8 times 10 to the 8 minus 3.0 times 10 to the 7 over the initial number, 3.0 times 10 to the 7, multiplied by 100. That gives us 500%. Now, this is actually a pretty easy question to do just kind of mental math. So remember, when we subtract exponents, the exponent has to be the same. And so to do this, you would just move this decimal over 1, and that would make this 18 times 10 to the 7. Now we're all in the same exponent. 18 minus 3 is 15. 15 divided by 3 is 5. So, 5 times 100, that's what gives us our 500. Notice, though, I still want to make sure that I put my percentage in the answer. So B, each mobile device sold in 2007 contained an average of 0.03 grams of gold. Calculate the number of grams of gold that were used in the production of the mobile devices sold in 2007. So it's telling us we need to pay attention to the 2007 number, which is this. So the 1.8 times 10 to the 8 number of devices. It also tells us how many grams of gold are present in each one of these devices. So I've got 0.03 grams per device. And that's really all that I need to know here. So let's look at the setup. So 1.8 times 10 to the 8 times 3 times 10 to the negative 2, because if I convert 0.03 in scientific notation, I'm moving it back 2 spaces. So that's 3 times 10 to the negative 2. Okay, that gives me my exponents, which allows me to easily solve this problem kind of with mental math. So 1.8 times 3, that gives me the 5.4. And then if I'm multiplying exponents, I'm really just adding them. So 8 plus negative 2, that gives me the 6. Notice I'm making sure to say grams. C, assume that the average mass of each mobile device was 0.1 kilograms. The United States Environmental Protection Agency estimates that about 10% of the mobile devices sold in 2007 were recycled. Calculate the mass in kilograms, so they're telling us exactly how they want us to show our answer, of the mobile devices sold in 2007 that were not recycled. So this is important here, because if I just jump the gun and say, oh, I'm calculating the 10%, then I'm not answering the question correctly. If 10% was the only amount that was actually recycled, that means 90% of it actually wasn't. And if I convert this percentage to a decimal, that's 0.9. So let's see how to set this up. So I've got 1.8 times 10 to the 8 devices, because I know I'm looking at the 2007 number. I know how many kilograms are in each device from the question here, 0.1. And then I also know from making sure that I'm reading correctly that I'm looking at the 90% that did not get recycled. So I'm going to multiply that by 0.9. And that gives me 1.62 times 10 to the 7 kilograms. Because, of course, devices cancel out. And then I've got all of that. So let's look at the last practice question. This is about area and volume. So coral reefs are produced when corals acquire calcium ions and carbonate ions from seawater and deposit solid calcium carbonate to form their exoskeletons. Scientists are concerned that relatively rapid decreases in ocean water pH will hinder the deposition of calcium carbonate. In order to model the effects of ocean acidification on coral reefs, some simplifying assumptions can be made. Now, again, if you notice, this is all about global climate change, global processes, ocean acidification. This is not content that you will learn until the very end of the course, but you don't need it because we just need to be able to do the math. So let's look at what assumptions they're giving us. We're going to assume that the total global area of coral reefs that grow are 2.5 times 10 to the 11 meters squared. We're going to also assume that there's vertical growth that is 3 millimeters a year, and then that the density of calcium carbonate in corals is 2 times 10 to the third kilograms per meter cubed. So already I'm starting to think in my mind, I'm going to have to be converting between meters squared, millimeters to meters, meters cubed. I'm dealing with area and volume. So what do they want us to do? Calculate the current annual global increase in volume in meters cubed of calcium carbonate in coral reefs. Calculate the current annual global increase in mass in kilograms of calcium carbonate in coral reefs. Because of ocean acidification, is it expected that in 2050, the mass of calcium carbonate deposited annually in coral reefs will be 20% less than is deposited currently? Calculate how much less calcium carbonate in kilograms is expected to be deposited in 2050 than would be deposited if ocean water were to remain at its current value. So let's look at A first. Calculate the global increase in volume, meters cubed. So I'm going to look over at my assumptions. The only thing that is in meters cubed right now is the density. And we're not worried about calcium carbonate yet. We're wanting to know the increase in the volume. So what do we know about corals? Corals have a global area of 2.5 times 10 to the 11 meters squared, and they grow at 3 millimeters a year. So if we want to know how much more calcium carbonate are going to be in the coral reefs, we have to know how much they're growing. So I know what the area is. I also know the vertical growth. So now I can calculate the volume in 1 year. Now, the only thing that I have to pay attention here is that this number is in millimeters and this number is in meters squared. So in order to get meters cubed, I've got to calculate meters, or I've got to multiply meters by meters squared. That means I need to convert this to meters. That's what this is doing right here. We know that there is 1 times 10 to the third millimeters in a meter. So that helps me cancel out my millimeters and allows me to get this answer right here. B, calculate the current annual global increase in mass of kilograms of calcium carbonate in coral reefs. Now, I know how much they have actually grown in a year. That's that annual global increase. And now they're wanting me to calculate how much calcium carbonate is in that growth. Well, we do have a conversion factor that they've given us for that, and that's 2 times 10 to the third kilograms per meter cubed. So how do I set this up? I take my answer from part A. So this is part A's answer, 7.5 times 10 to the 8 meters cubed a year. I take my conversion factor, which is in kilograms per meters cubed, and then I simply multiply. So meters cubed cancel out, and that gives me my kilograms per year that I'm making sure to write out. So now, again, I can kind of do this a little bit with mental math here. I can do 7.5 times 2, that's 15, right? 8 plus 3, that's 11. Well, 15, if I move it over one more time, that gives me an additional adding to my exponent, so that gives me 12. Because of ocean acidification, it is expected that in 2050, the mass of calcium carbonate deposited annually in coral reefs will be 20% less than is deposited currently. Calculate how much less calcium carbonate in kilograms is expected to be deposited in 2050 than would be deposited, if oceans were to be at their current level. So this is very similar to the previous question, in that they're wanting us to use data within the question itself and apply it to what we've already calculated. So we know how much is being deposited annually because we just calculated it. Now all we have to do is multiply that by the percentage, and that's how much, and that's how we are going to know how much would not be deposited if this were to come true. So that's that 1.5 times 10 to the 12 kilograms a year. I'm multiplying by 0.2. So you're basically, dividing this by 2, or you're getting a 20% of 15. That's 3. And that you move your decimal over one more time, and that gives you 10 to the 11 kilograms. All right, I hope that you have gotten a little bit more practice with doing the math calculations, and also see that it is definitely worthwhile to attempt them, because if you can do the math correctly, even if you don't know what the content is, you're guaranteed at least a few points on that question.